In this video, we are going to talk about the chi-squared distribution, which we're going to use for two different applications. This is our overview slide, which we'll spend about 5 minutes going over before we go over each topic in more detail and with more examples. The first thing we will do is introduce the chi-squared distribution. So the distribution is parameterized by something called degrees of freedom, much like the normal curve is parameterized by the mean and the spread, the standard deviation. So here are some different chi-squared distributions for different degrees of freedom. This blue curve is 2 degrees of freedom, the green is 4 degrees of freedom, and the red is 9 degrees of freedom. As the degrees of freedom get larger, the center, here you can see the center of each curve, moves to the right. So here's 2, here's 4 degrees of freedom moving further from here to the right, and here's 9 moving further over to the right. The variability increases. You can see this is stretched out over more space, and the distribution becomes more symmetric and less skewed. The mean of each distribution is equal to the distribution's degrees of freedom. The first application we'll consider for the chi-squared test is given a sample of cases that can be classified into several groups, determine if the sample is representative of the general population. For example, if we consider data from a random sample of 275 jurors in a small county, we can see if the jurors identify their racial groups, that the jurors are racially representative of the population. In other words, if the people in this county can be classified by races, and let's say the races are white, black, and Hispanic, we could see if the 275 proportions of white, black, and Hispanic matches the general population's proportions. And we do this using hypothesis testing. We calculate a test statistic, which is analogous to a z-score. We calculate this chi-squared, and if each count is at least 5, in other words, if there's at least 5 white, 5 black, and 5 Hispanic jurors, and if the null hypothesis is true, then our chi-squared follows a chi-squared distribution with k minus 1 degrees of freedom, where k is equal to the number of bins, or the number of categories. That is, if we have white, black, and Hispanic, we have 3 bins, so it's k minus 1, so 3 minus 1 is 2 degrees of freedom. Using this distribution, we'll be able to obtain a p-value to evaluate the hypothesis. We will also look at the conditions which make using the chi-squared test appropriate. One is independence, as we have for our other normal testing, and then we also have sample size distribution, which we had discussed over here about the counts. So each scenario must have at least 5 expected cases. And then finally, we'll look at a second application for the chi-squared statistical test, which is to evaluate whether data resembles a particular distribution, such as a normal distribution. Our example in this video will be comparing it to a geometric distribution. So that's it for our overview. So we can go back up here and take a closer look at the chi-squared distribution. Some general notes: the chi-squared distribution is sometimes used to characterize data sets and statistics that are always positive and typically right skewed. So you see there are no negative values, and they start to kind of trail off and skew to the right. The chi-squared distribution has just one parameter called the degrees of freedom, which influences the shape, center, and spread of the distribution. So this parameter, the degrees of freedom, is much like we have many different normal curves, and which exact normal curve we're talking about is parameterized by mean and standard deviation. Here we have 3 chi-squared distributions, and exactly which distribution we're talking about depends on degrees of freedom. So this blue one shows us a chi-squared with 2 degrees of freedom. Here we have in green a chi-squared distribution with 4 degrees of freedom, and then in red we have a chi-squared distribution with 9 degrees of freedom. And you can see as the degrees of freedom get larger, from the blue to the green to the red, the center moves to the right. Here you can see the center for the blue is at 0. The center for the green, it looks like it's somewhere closer to 3. And the center for the red, which is the 9 degrees of freedom, is over here somewhere around 7 or 8. The other thing is the variability increases. So in other words, the spread increases. You can see for 2 degrees of freedom, most of the data is over here, and it really shrinks down really fast. So it's within like maybe four units is most of the data. Whereas for the green, we have a lot of data probably going all the way out close to 10, 8 or 10, and then it starts to shrink really fast. Whereas 9 degrees of freedom, well, we're kind of still ramping up over here, but there's a lot of data over here, somewhere around 3, and it keeps going. We have still a significant amount of data, maybe till 12, and then it starts to shrink off. So there's more spread in the data. And last, the distribution becomes more symmetric and less skewed. So here the skew is to the right, and there's this long tail to the right. Here, there's a little more, little less skew, but we still have the long tail. And here we're starting to look less skewed. It's kind of actually almost looking a little more normal. So the mean of each distribution is equal to the distribution's degree of freedom. So the mean for here is equal to 2. So here is kind of the middle point of the data for the blue distribution. For 4 degrees of freedom, the green, the middle is somewhere over here. That's the mean. And the 9 degrees of freedom, the mean is somewhere over here, around 9, a little under 10. And just like for the normal distribution, we often look for area under the curve to determine the probability that a variable will take certain values or a certain range of values. For our first example, we're going to look at a chi distribution where degrees of freedom is equal to 3. We have a test statistic equal to 6.25, so we want to know the area under this curve. So since we're at 3 degrees of freedom, we're going to look at the row over here where degrees of freedom is equal to 3. You can see this column here has the degrees of freedom 1, 2, all the way up to 50. So now we want to find the column with 6.25. This is our z-score test statistic, and we see that the area associated with everything above, because this is the upper tail, so everything above 6.25 z-score is going to be 0.1. So that's our area. So this is it feels a little backwards from the normal curve, because usually we're looking up the z-score and then in the table are areas, whereas here we're looking up our z-score in the table and then finding the areas here. And in this case, again, this table is for the upper tail, as you can see over here. For our next example, we're going to look at a chi-squared curve where degrees of freedom is equal to 2, and we want to know the area in the upper tail above a test statistic of 4.3. So first we're going to look in the table at degrees of freedom equals 2, which we have in this row here. And we want to find the column with 4.3 in the test statistic. So when I look here, I have 3.22 and 4.61. So it's between these two test statistics. So what I can say is the area is going to be somewhere between 0.1 and 0.2. This table really doesn't give me anything more exact, so I can just give a range. Next, I have a chi-squared distribution where degrees of freedom is equal to 5, and I want to know the area in the upper tail for a test statistic of 5. So first I need to look up the degrees of freedom equals 5 row, which is right over here. And I want to find the entry for 5, but the smallest entry here in this row is 6.6, like 5 should be over here. But what I can see is the area gets larger, so that means we expect if we could get from 6, if we went down to 5, we would have something larger than 0.03. So the area is greater than 0.03. So let me just write greater than 0.03. And for my last example, we have a chi-squared with degrees of freedom equals 7 and a test statistic of 11.7. So I'm going to look up in the row degrees of freedom equals 7. And for 11.7 as my test statistic, I don't have anything in the 11s, but it's somewhere here between 9.8 and 12.0, which means my area is going to be between 0.1 and 0.2. Now that we've reviewed the chi-square distribution and how to use the table to find areas, we're going to look at our first application. Our first example is the one mentioned in our overview. We considered data from a random sample of 275 jurors in a small county. Jurors identify their racial group as shown below, so they can be white, black, Hispanic, or other. We would like to determine if these jurors are racially representative of the population. If the jury is representative of the population, then the proportions in the sample should roughly reflect the population of eligible jurors, of registered voters. While the proportions of the jurors may not precisely represent the population, it's unclear whether these data provide convincing evidence that the sample is not representative. It might just be sampling error. If the jurors were randomly sampled from registered voters, we might expect small differences due to chance. However, usually large differences may provide convincing evidence that the juries were not representative. So here we have our different racial groups, and then this is for the registered voters, the general population of that county. We expect 72% white, 7% black, 12% Hispanic, and 9% other. What we found is in our sample of jurors, 205 were white, 26 were black, 25 were Hispanic, and 19 people were other. It's kind of a strange table since this is given in percentages and this is given in number of people, but that's the data we have. Our first question, if the 275 jurors are selected at random, how many would we expect to be white? How many would we expect to be black? So we know the total number of jurors and we know the proportions according to the populations. So what we would say is we would expect out of the 275 jurors, we'd expect 72% or 0.72 to be white. So that will be 198. For black, of the 275 jurors, we expect 7% or 0.07, which is 19.25 jurors to be black. How many would we expect to be Hispanic or other race? So Hispanic or other race, that would be of the 275, 12% Hispanic, 9% other race. When we multiply it, we get 57.75 jurors, which would be Hispanic or other race. Now we're ready to do hypothesis testing. I've moved our data up here to give us more room. I also, for chi-squared, we're using this formula for the z-score, which is typical. It's observed minus expected divided by standard error. But we do have this standard error formula now that we need to use. It's different from our normal distribution. So standard error is the square root of the count from H0. So we will take a look at that in our example. So hypothesis testing now. Normally in hypothesis testing, our H0 is the one that is least alarming or not surprising. It's the boring one. The boring assumption is that our juries look just like our population, so the proportions will be equal. So H0, the jurors are a random sample, and any difference in observed counts represent natural sampling fluctuations. HA, the alternative hypothesis, is the jurors are not a random sample and that there is racial bias in jury selection. And the first thing we need to do is calculate our test statistic, which is analogous to a z-score. That's the score we're going to look up on our table. And we're going to use this formula here. This x squared or chi-squared is equal to the first observed value minus the expected value squared over expected value, plus the second observed value minus the second expected value squared over expected value, all the way up to the kth group. So the O sub I are the counts observed for each of the k categories. The categories here are white, black, Hispanic, and other. So there's k equals 4. and E sub I are the expected counts based on the null hypothesis. Each of these individual terms of our sum is Z sub I, so it's sort of like the Z-score kind of equivalent for each group or category. And this chi-squared combines these Z-scores for each of the categories. So let's take a look. On our previous slide, we had calculated the expected value for the white, black, Hispanic, and other groups. So it was 198. We expect 198 white people, 19.25 black people, 33 Hispanic, and 24.75 others. So our chi-squared is going to be our observed minus expected squared over expected. So our observed is 205 minus expected 198, all of that squared, over expected 198. For our second group, observed minus expected is 26 minus 19.25. We square that and put that over expected, 19.25. We take our third group, our 25 minus 33 squared over 33, and then our fourth group, other, so that's 19 minus 24.75 squared over 24.75, and we get a 5.89 for chi-squared. And again, each of these individually, these are our Z sub I. It's like the Z-score for each of the individual categories. And here our chi-squared combines them all. It sums them up. And the reason why we square them is we don't want these negative differences to cancel out with positive differences when we do the subtraction. Honestly, we probably should have done this step first, but for some reason in your book it wasn't listed till later, so I didn't either. But anyway, so we need to check to see that it's valid to use the chi-squared. So we need to see that each count is at least 5, and if the null hypothesis is true, then the chi-squared will follow a chi-squared distribution with k minus 1 degrees of freedom. So each count is at least 5. We see that. Each group has at least 5 people. In fact, we're well over. We're at 198, 19.25, 33, and 24.75. Because we have how many bins? 1, 2, 3, 4 bins. That means k equals 4. So our degrees of freedom is k minus 1. So we're at 3 degrees of freedom. And we're looking at our test statistic of 5.89, our chi-squared statistic. So I'm going to look in our table where degrees of freedom is equal to 3. So that's this row here. We're looking for a test statistic of 5.89. We don't have anything with a 5, so we're somewhere between the 4.6 and 6.25, so somewhere between 0.1 and 0.2. So our area is between 0.1 and 0.2, or 10% and 20%. We're going to use the area of 0.1171, which is 11.71%, and I got this from your book, which got it from some program. So our p-value is 11.71, which means if H0 is true, there's an 11.7% chance of getting a jury like our samples over here. And 11.7, that's a pretty good percent. It's not unlikely. So that means it's not an unlikely representative. This is something that we can expect to happen. So we do not reject H0, which means we cannot jump to the conclusion that there's racial bias in jury selection. It sure looks like it's okay. One more note, we're going to look at why we look at the one-way table, the one with only the upper tail. Suppose we are to evaluate whether there is convincing evidence that a set of observed counts, that O1, O2 up to OK in the K categories, are unusually different from what we might be expecting under a null hypothesis, the expectations being the E1, E2 up to EK. If each expected count is at least 5, and the null hypothesis is true, then the test statistic below follows a chi-squared distribution with k minus 1 degrees of freedom. And this again is our chi-squared test statistic. Each term in this sum is analogous to the z-score for each of the categories. So if this is the z-score of the first group, the z-score for the second group, up to the kth group. The p-value for this test statistic is found by looking at the upper tail of the chi-square distribution. We consider the upper tail only because larger values of chi-square would provide greater evidence against the null hypothesis. Next, we'll look at the conditions that we need to meet in order to use the chi-square distribution. The first condition will be familiar, it's independence. Each case that contributes to a count to the table must be independent of the other cases in the table. And the second condition is the sample size. Each particular scenario must have at least 5 expected cases, and failure to check these conditions may affect error rates. Last, we'll look at a second application of the chi-squared distribution. We'll evaluate whether a data set resembles a particular distribution, such as the normal distribution. The example we will use are daily stock returns from the S&P 500 can be used to assess whether stock activity each day is independent of the stock's behavior on previous days. We will label each day as up or down depending on whether the market was up or down that day. Days to up is the number of days that must be observed before each up day. That seems like a lot of up and downs in this sentence. So the idea is we want to know whether we can predict stock market behavior based on whether the stocks went up or down the previous days. So here we've talked about change in price over a particular day. And then we say, okay, here the change in price is positive, so it's an up day. The change in price is negative, it's a down day. Here we have positive up day, negative down day, positive up, negative down, negative down, negative down, positive up. And so remember, we want to know if the stock market is up one day, can we predict that the next day will be up? So what we're going to consider is this metric called days to up, and that's the number of days that must be observed before each up day. So here we had an up day, so there's 1. The down day doesn't count because it's down, but here we have an up. So how many days did it take to get this up? Well, this day certainly didn't predict an up day, but maybe 2 days back. Maybe this up day predicted this up day here. So we need to go back 2 days for the previous up. The down day doesn't count, but here's an up day. So we need to go back here 2 days. And that's where this 2 comes from, to get an up day. So maybe it's that once you have an up, then 2 days later you'll get an up. From here to here, that's sort of what it looks like. That's the pattern. But here we have an update, and it was predicted by the previous update, so only 1 day for the previous. Here's a bunch of down days, but here's another up day. So what day predicted this up? We have to go back 4 days. So again, this days to up is supposed to give us indication if whether or not the stock market being up 1 day can predict the next day. And here it looks like actually if you go back 2 days, you can predict an up 2 days later, but that pattern breaks over here. This one looks like a perfect predictor. The previous day was up, the next day is up. But here it looks like, wow, you have to go back way far, 4 days before you have the previous up. So it doesn't look like there's strong prediction in these days at all to predict the next up day, which isn't surprising. The stock market just goes up and down. But this is the metric, the measure they decided to try to determine whether or not there's any predictability to the market. And remember, the whole point is we're trying to determine hypothesis test, whether or not this is a good guess or not. I left my summary here to give us some space. And so one thing we need to determine is what distribution we're going to be looking at. Do we use the normal curve eventually? Do we use the chi-square? And the thing is, and we have to go back and remember our probability. So this was what, chapter 2, maybe chapter 3? I don't remember what chapter, but we have to go back to where we talked about geometric distribution, because this is probably a geometric distribution. I'll give you a brief review, but you might want to go back and take another look at that chapter. So if the days are really independent, then the number of days until a positive trading day should follow a geometric distribution. The geometric distribution describes the probability of waiting for the kth trial to observe the first success. So remember from probability, we had these things called Bernoulli trials, where we do something like flip a coin and we would have either success or failure. Maybe we'd define success as the coin coming up heads, and then failure would be tails, in which case the probability of a success or probability of heads would be 0.5. So that was a Bernoulli trial, but then we had something called a geometric distribution, which described the probability of waiting for the case trial to observe the first success. So we might need to, when we're flipping a coin, the first time we might not get a success, we might have to flip the coin 3 times before our first success. So that would be the probability of waiting for the third trial before we get a success. And we have a formula for that here. If the probability of success for our Bernoulli trial is P, then the probability of success in the nth trial is going to get to be 1 minus P to the n minus 1. This represents our n minus 1 failures because 1 minus P is the probability of failure, and we have n minus 1 of them, and then we need to multiply by P for our final success. So now we're ready to get into hypothesis testing, and we're going to test the hypothesis H0. The stock market being up or down on a given day is independent from the other days. So that's like our unexciting, like it'd be more exciting if we could say we could predict the stock market. But the H0 is usually kind of the pessimistic, unexciting news, which is the stock market goes up and down. It's independent from the other days. We can't predict one day from the previous ones. And we will consider the number of days that passes until an up day is observed. And under this hypothesis, the number of days until an up day should follow a geometric distribution. The alternative hypothesis is the stock market being up or down on a given day is not independent from the other days, and if we look for deviations from the geometric distribution, which would support the alternative hypothesis. So now we can introduce some real data so we can compare our observed stock data to what we would expect if the data follows a geometric distribution. So the S&P 500 was positive on 54.5% of the days in this study. So here are the days 1, 2, 3, 4, 5, 6, 7 plus. So then observed, these are the number of up days, and the geometric distribution predicted these numbers here. So again, these are our observed, these are our expected. You can see the expected values, if it were geometric, would be equal to 1 minus our 54.5% to the k minus 1 times our success, which would be 0.545. I moved that last chart up to give us more space. So here's our last chart again. And the points were the S&P 500 was positive on 54.5% of the day. So if we consider each day a Bernoulli trial, where a success is that the stock market is positive, then our probability of success is 54.5%. So I've made that note here. We're looking at number of days until there's an up. 1, 2, 3, 4, 5, 6, 7. So out of our total of 1,362 days, we see that 717, we observed that we only needed one day before to predict an up day. Here we had 369 cases where we had to go back 2 days for the previous up day. Here we had 155 cases where we had to go back 3 days for a previous up day. And then over here we had 7 plus, and we stopped putting 8, 9, and 10 because remember we need at least 5 cases for each category for Chi plus. So we used 10. So we grouped all our cases 7 or more days before you had the next up day. Here there were 10 of them. What a geometric distribution would have predicted for the 1,362 cases is that you would expect 743 days for K to be equal to, in this case, 1, or I guess, 1 day. There's 338 cases where you would expect K to be equal to 2 up to 7 plus. So expected values if geometric is equal to P of K is equal to 1 minus 0.45 to the K minus 1 times 0.045, again, because the 54.5% is the probability of success for the Bernoulli trial. So here we have our observed values. So O1, our first group, is 717, O2 is 369, and we go up to O7 is 10, and our expected value here is the geometric. Note, because the Chi framework requires expected counts to be at least 5, we have bin together all the cases where the waiting time is at least 7 days. We can calculate our test statistic using our chi-squared formula here. So we have our observed minus expected, so 717 minus 743 over our expected. Oh, and we have to square this. For our second group, we have 369 minus 338 squared over expected, and we do that for all the groups, and we get a chi-squared test statistic of 4.61. Our degrees of freedom is the number of groups minus 1, so that's going to be 7 minus 1 is 6. So we look up in our chi-squared table, and we see the area is 0.5951, which is equal to 59.51%. So the probability of seeing this type of distribution seems quite high, like 60%. So we do not reject H0, meaning there's not enough strong evidence to support that the days are dependent. There's no predictability. From our chi-squared testing, we tested the hypothesis that the stock market being up or down on a given day is independent from all other days, and that, in fact, it followed a geometric distribution, and we failed to reject this, so we see there's strong evidence that maybe it is a geometric distribution, and we can look at the graph of the expected versus observed, and it's hard to see if the distribution looks significantly different from a geometric distribution, which is why we needed to perform the chi-squared testing. To review what we have covered in this video, we looked at the chi-squared distribution, and first, the chi-squared distribution is parameterized by one variable called degrees of freedom, much in the same way that there are many different normal curves parameterized by the mean and then the spread or standard deviation. There are many different chi-squared distributions, and it's parameterized by degrees of freedom. As the degrees of freedom get larger, the center moves to the right, the variability increases, and the distribution becomes more symmetric and less skewed. The mean of each distribution is equal to the distribution's degrees of freedom. And here we have a picture in blue, a chi-squared with 2 degrees of freedom, in green, 4 degrees of freedom, and in red, 9 degrees of freedom. We looked at one application of the chi-squared test, and that is given a sample case that can be classified into several groups. We determine if the sample is representative of the general population. And the example we looked at is we considered data from a random sample of 275 jurors in a small county. We had the jurors identify their racial groups, and we wanted to determine if these juries are racially representative of the population. In other words, is the proportion of jurors for each race identical to the proportions of the population? And we did a hypothesis testing on this. We used, instead of a z-score, we used this chi-squared test statistic, which is essentially this. It's very similar to the z-score that we used for the normal curve, but we needed to square the top so we didn't have cancellations between negative and positive z-scores. And then we summed up all of these kind of z-score analogous calculations to get a chi-squared. The other thing we needed to verify is that each count was at least 5. So in this example, if we had 4 different racial groups, we had to determine there was at least 5 people in each racial group. So then we had the conditions for using the chi-squared distribution. We had to determine that the cases were independent, that if the case contributed to a count in the table, they had to be independent of the other cases. And 2, again, we checked the sample size to make sure each scenario had at least 5 expected cases. And then finally, we looked at a second application which allowed us to verify whether data resembled a particular distribution. A normal distribution would be one example. The example we looked at in this video was a geometric distribution. So that's it for this video. Thank you for watching.